Please do these theorems. First is eigenvalues corresponding to Hermitian matrix are all real. Corresponding to Hermitian matrix are all real. Then second is eigenvalues corresponding to skew Hermitian matrix. Matrix are all zero or purely imaginary. Third is eigenvalues for symmetric matrix are purely real, and for skew symmetric matrix purely zero or purely imaginary. Same, zero or purely imaginary. Please do these theorems. Why I am saying this? These theorems will appear in 3 or 4 marks. Now, one more is Cayley-Hamilton theorem. Please do this theorem also. Cayley-Hamilton theorem. I mean the proof of the theorem. Obviously, we are talking about the proofs. One is eigenvectors corresponding to distinct eigenvalues of Hermitian matrix are orthogonal with respect to each other. With respect to most important result, please do the proof. Next is, I will do this 7th part. Eigenvalues corresponding to distinct eigenvectors corresponding to distinct eigenvalues of a linear operator are linearly independent. Okay, are linearly independent. So what I am saying with proof I am doing this, because all these results belong to matrices and this result belong to a linear operator. So linear operator is the thing which we are doing in this class. That's why I am doing the proof. The proof says that let phi from V to V is a linear operator and lambda 1, lambda 2 up to lambda n be its distinct eigenvalues and v1 v2 up to vn be corresponding eigenvectors. Then phi vi is equal to lambda I vi for all I from 1 to n. I hope you are clear with this. Now, what I am trying to say, what we want to prove? We want to prove that let alpha 1, alpha 2 up to so on alpha n belong to F, so that alpha 1 v1 plus alpha 2 v2 plus up to so on alpha n vn is equal to 0. What we want to prove? We want to prove that we will be having a linear operator. Linear operator will be having distinct eigenvalues. When it will be having distinct eigenvalues, all eigenvalues will be having their corresponding eigenvectors, and these eigenvectors should be linearly independent. This thing we want to prove. Now I have these vectors v1, v2 up to so on vn. These vectors are there and they belong to distinct linear eigenvalues, and I want to prove that these are linearly independent. How we prove that vectors are linearly independent? We take their linear combination, we put them equal to 0. We want to prove that alpha 1 is equal to alpha 2 up to so on is equal to alpha n is equal to 0. If we prove this thing that all these alphas are 0, then these vectors will be linearly independent. I hope this thing is clear to you. Is this clear? It can say that you have a linear operator. Linear operator is from one vector space to other vector space. Okay, obviously we know that a linear operator is always from one vector space to the same vector space. Now, by the definition of eigenvalues, we know that when we have a linear operator, we put v in this and it becomes lambda v. We say, and this v should be non-zero. This v should be non-zero. We say that this small v is eigenvector of linear operator. You know this. Now, what happens is, this is one vector v1. When I apply phi on it, it becomes lambda 1 v1. Then we have another vector v2. I apply phi on it, linear operator on it, and it becomes lambda 2 v2. Then I have another vector v3. I am finding these vectors v1, v2 up to so on these vectors. When I apply phi on these vectors are becoming eigenvectors corresponding to the eigenvalues lambda 1, lambda 2 and lambda 3 and up to so on, and these eigenvalues happens to be distinct. One thing. Now what I want to prove that these eigenvectors v1, v2, v3 up to so on vn, they will be linearly independent. We want to prove this thing. Now, how we prove the what is the definition of linearly independent vectors? Okay, definition of linearly independent vectors says you have v1, v2 up to so on vn. These elements are there in vector space. Now alpha 1, alpha 2 up to so on alpha n are the field, are the scalars. Now you take linear combination, it becomes alpha 1 v1, alpha 2 v2 up to so on alpha n vn. You put it equal to 0. When you put it equal to 0, becomes all scalar become equal to 0. Then you say that the vectors are linearly independent if some particular or anyone, if at least one alpha I is non-zero, then we say that the vectors are linearly dependent. I hope you know these definitions. Do you know these definitions? Okay, clear. Okay, I hope it is clear to everyone now. So whenever you are doing a theorem, always remember that you should know which thing is given to you and which thing you want to prove. Okay, now you say that you have a linear operator. Linear operator is from v to v, fine. Then you have eigenvalues. Eigenvalues are distinct, fine. You have eigenvectors correspondingly v1, v2 up to vn, fine. Then you have obviously the definition of eigenvalues and eigenvectors, this thing. Now we want to prove that the vectors v1, v2 up to so on are linearly independent. If we want to prove this thing, then we have to prove that the scalars alpha 1, alpha 2 up to alpha n are 0, simply. Okay, now the thing is we will prove this theorem by PMI, principle of mathematical induction. Now for n is equal to 1, this is your thing. You take linear combination is equal to 0 and you want to prove that all scalars are 0, then you prove the result. So you take n is equal to 1. When you take n is equal to 1, this is alpha 1 v1 is equal to 0. Now this v1 is not equal to 0. Why this is not equal to 0? Because this is eigenvector. If it is eigenvector, then it cannot be 0. Now v1 is non-zero. Two things are making, I mean, product of two things is equal to 0. One is non-zero, so other will be equal to 0. So alpha 1 is equal to 0. Therefore, for n is equal to 1, result is true. Result is true. Fine. Then you say for n is equal to k, we suppose result to be true. We suppose result to be true. We suppose result to be true. So this means that whenever alpha 1 v1 up to so on alpha k vk is equal to 0, then alpha I will be equal to 0. I hope this is called induction hypothesis. Now for n is equal to k plus 1, we have to take alpha 1 v1 alpha 2 v2 so on alpha k plus 1 vk plus 1 is equal to 0. Fine. We apply phi on it, phi on whole thing equal to phi 0. So you see this becomes alpha 1 phi y1 alpha 2 phi v2 up to so on alpha k plus 1 phi vk plus 1. This thing is equal to, because 0 will always go to 0, you know this. I hope this thing is clear to you. So this thing becomes alpha 1 lambda 1 v1 alpha 2 lambda 2 v2 so on alpha k plus 1 lambda k plus 1 vk plus 1 equal to 0. Clear to everyone? Now you have, for example, you have this, I consider this thing is equal to 1 and this thing is equal to 2. What I am doing is I take 1, multiply it by lambda k plus 1 and subtract 2 from this. Okay, simply multiply this thing by lambda k plus 1. This thing will become alpha 1 v1 lambda k plus 1 lambda k plus 2 plus 1 alpha 2 v2 up to so on lambda k plus 1 alpha k plus 1 vk plus 1. This thing is equal to 0. First of all, you have this thing, multiply this thing by lambda k plus 1. Clear everything? So now you have this thing is 2, this is alpha 1 lambda alpha 1 lambda 1 v1, then alpha 2 lambda 2 v2 up to so on alpha k plus 1 lambda k plus 1 v k plus 1. This thing is equal to 0. Okay, this thing is equal to 0. You subtract this, negative 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 negative, all signs will change. It will become, okay, it will become alpha 1 lambda 1 minus lambda k plus 1 and v1, then alpha 2 lambda k plus 1 v2, then up to so on alpha k lambda k plus 1 vk is equal to 0. I hope this thing is clear to you. This last term is getting cancelled, all other things are as it is. Now you say that by induction hypothesis, whenever you have a linear combination of k factors v1 v2 v3 up to so on vk, whenever you have linear combination of k factors and those things are taken in linear combination and put equal to 0, then these scalars will become 0. Now in this we have v1 v2 v3 up to so on vk. these things we have, and these things are in linear combination with respect to some scalars and put equal to 0. Induction hypothesis says that if you take linear combination of k factors and put them equal to 0, then these scalars will become equal to 0. I hope this thing is clear to everyone. So it becomes implies by induction hypothesis. This implies what this implies? This implies alpha I lambda I minus lambda k plus 1 is equal to 0. I hope this thing is clear to you for all I. For all I, and this I varies from 1 to up to so on k. Okay, if it is not clear to you, you can write it as, we don't know that whether this result will happen for k plus 1 or not, but we know that the result will happen for k. This means that if you have k vectors and the linear combination is equal to 0, then the scalars will definitely become 0. So you say alpha 1 lambda 1 minus lambda k plus 1 is first scalar, this will be equal to 0. Then you say alpha 2 lambda 2 minus lambda k plus 1 is equal to 0, this is second scalar, this will be equal to 0, up to so on alpha k minus lambda k minus lambda k plus 1 is equal to 0. So that now I hope this thing is clear to you. I should ask this, is this clear? So the thing is, these scalars are equal to 0. You say, when you start, you say this, that that these eigenvalues are distinct. These eigenvalues are distinct means lambda 1 is not equal to lambda 2, is not equal to lambda 3, is not equal to up to so on lambda k plus 1. Or okay, if they are not equal, then lambda I minus lambda k plus 1 cannot be equal to 0. This thing is very obvious to you. So what I am trying to say is, this thing, product of two things is equal to 0. One thing says that I am not 0. Product of two things is 0. One thing says I am not equal to 0. Product of two things is 0. One thing is not 0. So this means that alpha 1 is 0, alpha 2 is 0, up to so on alpha k is equal to 0. Alpha 1 is 0, alpha 2 is 0, up to so on alpha k is equal to 0. So you put this result, alpha 1, alpha 2, alpha 1 is equal to 0, 2 is equal to 0, up to so on. Everyone is equal to 0 in 1. This is 1, I rubbed it by mistake. Alpha 1 v1 up to so on alpha k plus 1 vk plus 1 is equal to 0. You know that alpha 1, alpha 2 up to so on alpha k all are 0. This means alpha 1, alpha 2 up to so on alpha k, all these things becomes 0, and it becomes alpha k plus 1 vk plus 1 is equal to 0. But vk plus 1 says I am not 0. If he is not 0, then alpha k plus 1 will have to become 0. I hope this thing is clear to you. So you say hence or therefore alpha 1 is equal to alpha 2 is equal to up to so on alpha k plus 1 is equal to 0. Therefore result is true for n is equal to k plus 1, and hence result is true for all n belonging to natural number. Hence the result is proved by a principle of mathematical induction. Is this clear to you? What happens? What are you saying? we assume the result that whenever you will be having, see what I am doing in what we are doing in this proof is, we are proving that when you will be having a single eigenvector, it will be linearly independent. PMI says prove the result for n for some finite value, for example like 1, 2, 3. You prove the result for n is equal to 1. Then you assume the result for n is equal to k. If you are getting confused with this, I should write that for n is equal to k, we assume the result to be true. This means that whenever you have k vectors, those k vectors will be linearly independent. Alpha is just representative of linear independence. These alphas which are taken in n is equal to k are not same as that which we have taken in n is equal to k plus 1. N is equal to k plus 1 is completely new step. Okay. For then you take, see, you prove that a single vector is linearly independent. Fine. Then you prove that if you have k vectors, these k vectors will be linearly independent. Okay, these k vectors, we assume this thing that whenever we have k linear k vectors, those k vectors will be linearly independent. Now you have n is equal to k plus 1. When you have n is equal to k plus 1, you want to prove that if you take a set of k plus 1 vectors, that set will also be linearly independent. Okay, so you take linear combination of these k plus 1 vectors and put them equal to 0, and now our aim is to prove that all alpha 1 to alpha k to alpha k plus 1 will all be equal to 0. These alphas which are being used in this step of n is equal to k plus 1 are not same as that used in n is equal to k. Is this clear to you? One minute. I can simply say that we suppose the result to be true for n is equal to k. We suppose the result to be true, i.e. a set of k vectors will be linearly independent. We can write in this way also. Okay, we can write in this way also. A set of linear independent vector will be linearly independent. Okay, now you say that this is okay. Now I think this is clear. So you will say that all these alpha 1, alpha 2 up to so on alpha k plus 1 are equal to 0. So what it means? It means that k plus 1 vectors are also linearly independent. K plus 1 vectors are also linearly independent. So you start with n is equal to 1, then you take equal to n is equal to plus 1. This is Pm. So you say hence by principle of mathematical induction, the result is true for n is equal to principle of mathematical induction hold all n belonging to natural number. I hope it is clear now.